Hey AP Stat students, this is Mrs. Brookshire from Glenver, and I'm going to be covering section 5.3 with you today, part 1. This whole section is on conditional probability. It's broken up into 3 parts. Today we're going to be talking about how do you calculate and interpret conditional probabilities and how to determine if two events are independent. Okay, first of all, what is a conditional probability? It's probably what you think it is. Conditional means there's a condition, okay? So in an earlier example, we used a two-way table to find probabilities involving events. So we're going to let A be the person's male, B, this is the pierced ear problem. B, the person has a pierced ear for a randomly selected student in a statistics class. So recall, how do you find the probability of A? And that's what's probability that he is male. So it is 90 out of 178. What's probability that the person selected has a pierced ear? 103 out of 178. What's the probability of male and pierced ear? Here's your male pierced ear, so it'd be 19 out of 178. What's the probability of A or B? Don't forget that this was one of our rules that we learned in the last section, that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Because if you counted this and this, you would be including this number, so we kind of had to subtract out that overlap. So the probability of A was 90 over 178, probability of B is 103 over 178, minus 19 over 178, which gives you 174 out of 178. So this is just kind of a refresher of what we did last when we were finding probabilities in a two-way table. If we know that a randomly selected student has a pierced ear, what's the probability that the student is male? This right here is a condition. If we know that the randomly selected student has a pierced ear, that is a conditional statement, okay? What's the probability that the student is male? So what we're going to do is I'm going to kind of show you. So it's male given pierced ear. So anytime you see that in statistics, you'll see this line. So the probability of male given pierced ear. So what you're going to do is male given pierced ear is going to be 19 out of given pierced ear would be your yes total, which is 103. So it's 19 out of 103. Okay, so when you find a conditional probability in a two-way table, you want to find given and pierced ear goes on top, which is 19, and then the probability of a pierced ear, which you would use the 103, which gives you 0.184. Okay, so if you kind of think about it, it's really 19 out of 178 over 103 out of 178. Well, what happens is when you do this, those 178s cancel, and that's why we can just use the 19 out of the 103. Okay, so if we know a student selected is male, so this time that's the condition. If we know they're male, what's the probability that the student has a pierced ear? So the way you would write that is probability of pierced ear given male, or you're probably going to use that line, probability of pierced ear given male. So pierced ear and male goes on top, which is 19, and then the male total goes on the bottom, okay? So that's what you're going to see if you have a conditional probability. This is the definition of conditional probability. The probability that one event, the probability that one event happens given that another event is known to have happened is called a conditional probability. The conditional probability that event B happens given that A happened is denoted B given A. So the conditional part always goes behind the line, whatever the given is, given whatever, that goes behind the line, and then the other event goes in front. So there is a formula that you can use, and this formula is on the AP formula sheet. So anytime I see, and I realize I have a conditional probability, I will write this formula out. So it's probability of A given B is probability of A and B, which we can denote by that. We know that A and is the intersection because they're both happening at the same time. and then the probability of B goes on the bottom. And kind of the way I remember that is, I don't know, just the B is second, so I just remember that that goes in the denominator. This is how you will see it on the formula sheet. If you go look under probability, this is the conditional probability formula. Okay, now you don't have to use A and B. You can use other letters if it helps you. All right, so here is the next example that we're going to go through. It says, in 1912, the luxury liner, the Titanic, on its first voyage across the Atlantic, struck an iceberg and sank. Some passengers got off the ship in lifeboats, but many died. Suppose we randomly select one of the adult passengers from the Titanic. Okay, F is that you were a first-class passenger, S is you survived, and T, you were a third-class passenger. So it says, find the probability of T given S and interpret this value. So T was third-class passenger. So what it's asking us to do is find the probability that you were a third-class passenger given you survived, okay? So again, I'm going to think about this formula. And instead of using A and B, we're going to use T and S. So what you're going to write is the probability of T and S over the probability of S. And you can see that that's what I wrote down. So the probability of T given S is the probability of T and S over the probability of S. And again, in a two-way table, you can just find that particular number. So T and S would be right here, 151. And then your denominator probability of survived would be this number right here, the 442. And I kind of showed you the fraction thing again. But again, when you're using a two-way table, you don't have to use a denominator because those will cancel. So you can just use T and S, and then the probability of S, just use that number there, okay? So what does that mean? Well, if I asked you to it asks you to interpret this value, you would say, given that a randomly chosen person survived, because that's the given part, given that a randomly chosen person survived, there is a 34.2% chance that he or she was a third-class passenger. Okay, so that's how you want to write that out. Given that a randomly chosen person survived, there is a 34.2% chance that he or she was a third-class passenger. So that would be our interpretation of what this says. Given that a randomly chosen person survived, like if you're talking about all the people and you pick one person's name, given that they survived, there's a 34.2% chance that he or she was a third-class passenger. Okay, so that's part A. Part B, given that the chosen person is not a first-class passenger, how would we write that? If a third-class passenger is T. And also, that's your given part. That's your conditional. So you would do T complement. That would be your conditional part. What's the probability that she or he survived? Write your answer as a probability statement using correct symbols for this event. Okay? So what you would want to say is not a first-class passenger. Sorry, I said third. It's first. So if first class is F, not a first class would be F complement. So that's what I wrote here. That's your given part. That goes behind the line. What's the probability that you survived? That they survived? Whoopsie, let me scoot this up a little bit. I kind of had this printed out so we could kind of run through it in this fashion. So the probability of survived given not a first class passenger. Well, our formula says up here, if you have a conditional statement, it's the probability of both divided by the probability of not first class. On this one, you've actually got to go up and say survived and not first class. So you want to go to the survived line. Here's first class, so you need to pick these two. So that's why I'm adding those two. And then on the denominator, probability of not first class. Here's your classes, and so not first class would be not this one, but it would be these two. So on this one, you actually have to add these two numbers, and that gives you 245 over 888, which is 0.276, okay? So that is how you would find that probability. So the big thing to remember is anytime you see the word if you see the word given, you have a conditional probability. The conditional part goes behind the line, and then the other part of the probability problem goes in front. And then it's always the probability of both things happening over the probability of this. This would always be in your denominator. All right, so we're going to do a couple more examples here. The next one, I think that we are, yeah. Okay, there is an AP stat, like a tip here at the top, and this is important because a lot of times you're just really inclined just to write the answer. Please don't do that. Many students lose credit on probability questions because they don't show their work. You don't have to show the formula. That's not required. I think it helps, but students should show the numerator and denominator of the probability. So please do at least that. All right, the next question. A survey of all 38 residents in a large apartment complex reveals 68% use Facebook. So I said probability of F is 0.68, 28% use Instagram, probability of I equals 0.28, and 25% do both. Probability of Facebook and Instagram is 0.25. Suppose we select a resident at random, given that the person uses Facebook. So guess what? It's going to be the probability given that they use Facebook. What's the probability that he or she uses Instagram? So that's what we're going to go find. This is a conditional probability. See the word given? Okay, this is conditional probability. So think about your formula, and we don't have to use A and B here, but what we're going to do is our formula is going to be the probability of both divided by the probability of Facebook. Now on this one, we don't have a two-way table. We just go use these values here. So both is 0.25, Facebook's 0.68, and then that would give you a 0.368. Please be careful and put the conditional part behind the line, because if you don't, you will get a different answer. And I think that's what we're going to do next. Refer back to this example. If the person chooses to use, is an Instagram user. So again, that's going to, the conditional part, that goes there. What's the probability that they use Facebook? Okay. Go look at your formula if you don't have it memorized. So you're going to do the probability of Facebook and Instagram over the probability of Instagram. And when you go through and you do that problem, you get the 0.25 and then the 0.28, and you do get two totally different answers. So please make sure you pay attention to the conditional part. It goes behind the line. And then when you use your formula, it's always the probability of both things happening, and then the probability of that goes in the denominator. Okay, you can write statements like probability of A given B if events A and B are clearly defined in a problem. Otherwise, it's probably easier to use contextual labels like probability, like we did up here. Instead of A and B, just use F and I, okay? Or you can also just use words if you want to. You don't even have to use the letters. Okay, we have one more example on this, and then we're going to go and talk about independence. Okay, it says Yellowstone National Park surveyed a random sample of 1,526 winter visitors to the park. They asked each person whether he or she owned, rented, or had never used a snowmobile. Respondents were also asked whether they belonged to an environmental organization like the Sierra Club. The two-way table summarizes the survey responses. So, in the environmental club, yes or no, yes or no. Snowmobile experience, never used, renter, or owner. Okay. Suppose we randomly select one of the survey respondents. So we're going to pick one of these people. E stands for environmental club member, that they are. S stands for snowmobile owner, and N stands for never used. So number one, find the probability that they never used a snowmobile given they are in the environmental club, in an environmental organization, and interpret this value. So when you think about that, do you think that value is going to be high or low? never used a snowmobile given they're in an environmental club. I don't know that they really appreciate snowmobiles if you're an environmental club member. So we'll see what happens here. All right, so probability of first thing I did, look what I did is I wrote down the formula. Probability of N given E is the probability of both divided by the probability of E. So what's N and E? Never and yes is 212. And then the probability of E is 305. So it's 212 over 305, which is 0.695. Okay, so that is what you do on a two-way table. So let's interpret this. Given that a survey respondent belongs to an environmental organization, there's about a 69.5% chance that he or she never used a snowmobile. Okay, so that's how you would interpret that. Given that a survey respondent belongs, that's the given part, you want to list that first, belongs to an environmental organization, there's about a 69.5% chance that he or she never used a snowmobile. Okay. All right, question 2. Given that the chosen person is not a snowmobile owner, So that would be complement of S. What's the probability that he or she is an environmental club member? So that is going to be so basically what we're doing here is finding the probability. That's your given part. So that goes behind the line like that. So given that the person is not a snowmobile owner, that's our conditional, what's the probability that he or she is an environmental club member? Write your answer as a probability statement using the correct symbols for the event. So they want us to write it. So that's how you would start it off. So don't forget our formula. You're going to do this and this divided by the probability of that. Okay? So the probability of E given not, whoopsie, let's move this up a little bit. So here is our formula. And again, I think it helps, goodness, especially on one like this, to write this out, okay? So, probability of both over the probability of that. So, environmental and not. So, yes, but not a snowmobile owner. You need to add these two, the 212 and the 77. And then not a snowmobile owner, you need to add these two. Okay, and that's how I came up with that, and my answer is 0.235. Okay, all right, number 3, is the chosen person more likely to not be an environmental club member? So this is not. Is the chosen person likely not to be an environmental club member if he or she has never used a snowmobile, is a snowmobile owner? So the conditional part is actually where it says the part after the if they never used a snowmobile. So the first one is kind of crazy. So it's like, so what you're going to do basically is you're going to find each of the 3 probabilities. I didn't read through the whole answer or through the whole question. So is the person chosen more likely to not be an environmental club member if he or she has never used a snowmobile, is a snowmobile owner, or a snowmobile renter? Justify your answer. So to justify, you're just going to go through and you're going to show these 3 different probabilities. So the first one is the probability not in the environmental given never used a snowmobile, which is your N. So when you look at your table, you're going to do the probability that both. So not in environmental, so you're going to go to the no column and never used a snowmobile. That's your 445, and then the denominator is a no, which is, or never used a snowmobile, which is 657. So that's that answer. The next one is that given they are a snowmobile owner, so same thing, given snowmobile. So if you look in here, this is your no, and a snowmobile owner, which is 279 over Snowmobile owner is $295. Okay, 0.946. And then the last one is renter. So it would be the probability of not an environmental organization given a renter. So the same thing here. It'll be 497 over the 574. So this is our highest probability. So we justified our answer, but the final answer is the person is more likely to not be an environmental club member if he or she owns a snowmobile, which makes sense. Okay. The person is more likely not to be an environmental club member if she or he owns a snowmobile. So there's our highest probability. Okay, the last thing we're going to do is we're going to go through and show how we can use conditional probabilities to prove that two events are independent. Okay, and that is the remainder of the lesson. So let's go through this. All right, A and B are independent events if knowing whether or not one event has occurred doesn't change the probability the other event will happen. In other words, events A and B are independent if. These are kind of like little math formulas here. Like this is how you can show independence. You can either do probability of A given B is equal to the probability of A given not B. You can also do the probability of A given B is equal to the probability of A. Or you can do the probability of B given A given probability of B given not A if those two are equal. Or you can do this equals if those two things are equal. So kind of let me explain what independent means to me. Okay, let's say that you are drawing two cards from a deck. Okay, if I am going to pick two cards and I say, what's the probability of getting two aces? Really, it depends. If I say that I'm putting my card back in the deck, then those two events would be independent because the second card would have nothing to do with the first card because it wouldn't matter what I picked for the first card because I'm putting it back in. But they would not be independent if I didn't replace the cards. Okay, so that's a situation of independence. But you can actually go through and prove mathematically that you have independence by using one of these formulas. So we're going to go practice that a little bit. Is there any relationship between gender and subject preference, math or English? The two-way table summarizes the relationship between gender and subject preference for a class of 25 AP Stats students. Suppose we choose one of the students in the sample. Are the events math and male independent? Justify your answer. Okay, so we've got this two-way table here, and we're trying to show that they're independent or not. Well, here's the answer, but we're going to go through and show why. So what you can either do, there's a couple things you could do. If you're comparing math and male, you can, and what I did is I said A was male and B was math, that they prefer math, okay? So what you can do is because a lot of people are going, well, do I do like A given B or give B given A? Honestly, it doesn't matter, okay, to show independence. So I'm kind of going to show you both. So what I did first is I found the probability of A. Probability that you have a male is 10 out of 25. Then I went and found the probability of A given B. Given that they like math, they're male. So this is one of the ways, if you look up here at the table, this is one of the ways you can find probability. So what I was doing here is I was showing A given B is equal to the probability of A. Okay? If you show that, you have independence. So we do come out that they are equal. So then if I did it the other way, I was doing the probability of B given A is equal to the probability of B. And here's the probability of B, here's B given A, and again, they're equal. So therefore, math and male are independent. So those two things are independent, and I just proved it right here. Okay, so that is one way that you can show independence. Another way you could do it is you could do A given B and then A given not B. If those two are equal, you have independence. You don't have to do all three things. It's kind of like two parts. Either do that or do that middle part or these two. So the next example we're going to look at, it says, let's take a look at our earlier the ear piercing thing. So what we're trying to do is show if being male and having a pierced ear are independent, okay? So what we could do is either we could do probability of A given B is equal to the probability of A. The other thing we could do is the probability of A given B is equal to the probability of A and not B, okay? So I think on this one, the probability of B given A, well, we did it backwards, but either way is fine. Pierced given male would be 19 out of 90. And then the probability of pierced and then female would be the conjugate is 0.955. So obviously these two are not equal, okay? So knowing this tells us that they're not independent. Knowing that chosen student is a male greatly reduces the probability that the student has a pierced ear, so these two events are not independent. And then another way, like I said, this is another way you could also do it. You could do probability of A given B, does it equal to the probability of A? So I found what that was equal to, and I found the probability of A, and they're not equal. You could also do the probability B given A is equal, and testing it to see if those are equal, and they're not equal either. So anyway I worked that problem out, I did not have that they were independent. Therefore, being male and having pierced ears are not independent, which was stated here. Okay, these are the way to show independence. Probably A given B, which is really what we just wrote up here. And then A given B. So either one of these or either one of these, which is what we had just talked about up in the box up there. All right, so we're going to go through and we're going to do two more quick examples and then we'll be finished. So as you can see, showing that two things are independent can be proven by our conditional probabilities. Okay, this is gender and handedness. Is there a relationship between gender and handedness? To find out, we use census at school's random data selector to choose a simple random sample of 100 Australian high school students who completed a survey. The two-way table summarized their relationship. So they asked, or they found out what the gender was and then if they were left or right-handed. Suppose we choose one of the students as at random. Are the events male and left-handed independent? Justify your answer. So I said the probability of left-handed given male would be the probability of left-handed and male, which is 7, over the probability of male, which is 46, which is 0.152. And then I just did probability left-handed given female. If those two were equal, they would be independent. So left-handed and female would be 3 out of 54. Those are not equal. Therefore, we can say that they are not independent, okay? Because these probabilities are not equal, the events male and left-handed are not independent. Knowing that the student is male increases the probability that the student is left-handed in this data that we have. Okay? Another way you could do this, you could do the probability of left-handed given male is equal to the probability of left-handed. And it's kind of weird on this because it's always, if you're going to do it that way, it's the probability of left-handed given male equals, and it's always the probability of the first thing. Okay, so that would be another way. One more example. Oh, this is a good one. Because this one, you're just going through the first two and telling why they are or not independent. You're not really doing any math. And sometimes that's what you do. So like it says, for each random process given, determine whether the events are independent. Justify your answer. Number 1, shuffle a standard deck of cards and turn over the top card. Put it back in the deck. Shuffle it again and turn over the top card. Define event A as that you get a heart, and then B, the second one is a heart. Do you think those are independent? We've already kind of talked about this. The answer is yes, because you replace the card. Events A and B are independent because we are putting the card back before drawing the second card. Knowing what the first card is not going to help predict the second card because you're putting it back. Number 2, shuffle a deck of cards, turn over the top 2 cards one at a time. Now, those two would not be independent because the probability of getting a heart on the second card could change based on the first card drawn. So if you picked a heart and then you said, okay, pick another one, and you picked a heart again, that probability would change because you're not replacing the card. And then the last question, anytime they give you a two-way table, you're going to have to do some math to show independence. The 28 students in Mr. Tabor's AP Stat class took a quiz on conditional probability independence. The two-way table summarizes the class's quiz based on gender and whether they got an A. Choose a student from the class and show that if female and getting an A are independent. So what I did first is I just went through and totaled everything. And I believe we're going to do probability of getting an A and seeing if probability of getting an A given female gives you the same probability. And it does. You could also do the probability of got an A and male. Okay, let's see what that is. So probability of got an A in male would be 1 out of 7. So all these are equal, okay? So you could compare these two, or you could compare these two. Remember, it was probability got an A given female and the probability got an A. So therefore, the two events got an A and female are independent. So you could either do it this way or you could do it this way. Either way, you got the same probability. And that is the conclusion of conditional probability, how to find it, the exact value, and then also how to use conditional probability to show that two events are independent. There are 2 more videos that we will be discussing. See you soon.